Hi, I'm Thea Kozakis. I'm a postdoc at the Technical University of Denmark, and I'm going to talk a bit about work I've been doing to assess whether O3 is a reliable proxy for O2. So to start off, why would we want to use ozone as a proxy for O2? And the answer to this is summed up in this figure here, which was in the white paper for the LIFE mission. And it's about the retrieval of Earth-like atmospheres, and it's showing which molecules and planetary quantities can be retrieved with the thermal emission spectrum, which is what the LIFE mission would do, or in a reflected light spectrum. And you can see here that in thermal emission, all of these parameters can be retrieved except for O2, molecular oxygen. And considering that one of our most promising biosignatures is O2 and CH4 together, we would definitely like to be able to assess the O2 content of a planetary atmosphere. So a workaround that people have spoken about is instead of using O2, using O3, ozone. And that's because O3 is a photochemical product of O2. And I'll explain that more here. In an Earth-like atmosphere, ozone is primarily created via what we call the Chapman mechanism, which the reactions you could see right here. So these are highly dependent on photolysis, so just a photon coming in and breaking apart a molecule. So what we do is we start off with an O2 molecule. It gets hit by a photon. What's important here is that the photon has to have a wavelength of less than 242 nanometers. And that's because it needs to have enough energy to break apart the O2 molecule. So if you have that, O2 can be broken up into these oxygen atoms. One of the oxygen atoms can recombine with an O2 molecule and make O3, ozone. Right here, the M is just a background molecule to carry away excess energy, and that could be something like nitrogen. After you do have O3, it can be converted back into O2 either via photolysis of O3 or by combining with an oxygen atom, at which point you can start the cycle again. And something important to note here is that even though these reactions might seem simple, O3 production is not linearly related to the O2 content of an atmosphere. And also importantly is that you may have guessed, this is very dependent on the amount of UV flux reaching the planet, especially because this first reaction, the photolysis of O2, requires a high energy UV photon. So let's return to my original question, which is, how reliable is ozone as a proxy for O2? And to help answer this question, I'm going to break it up into some mini questions that I'll discuss throughout the talk. So first of all, how have O2 levels changed throughout Earth's history? And what was life like on Earth throughout Earth's history? How does ozone change as a function of O2, not only for the Earth-Sun system, but also around different types of stars? And then finally, how would these different O2 levels around different types of stars change the O3 emission features? Because in the end, what we want is to know, by looking at O3 emission features, can we back out information about O2 content? So we'll start with asking ourselves how O2 levels have changed throughout Earth's history. And I know that this is a complicated diagram. I'm going to go over it briefly, but if you're more interested in this subject, you could either talk to me offline, or you could read this review that the figure's from, which is a very great review. So here you can see our estimates for O2 throughout Earth's history. And the units here to measure O2 is in this unit PAL, which that stands for present atmospheric level. And you'll see this abbreviation a lot during the talk. So initially there was very little O2 in Earth's atmosphere until about 2.5 billion years ago. There was a big jump in O2, which we call the Great Oxidation Event. And after that, O2 people estimate could have jumped to between 1 and 10% our present atmospheric level of oxygen. Also, for reference, our present atmospheric level for oxygen in Earth's atmosphere is that O2 is about 21% of our atmosphere. Later on, about 500 million years ago, we had the lesser oxygenation. So there was another jump in O2, perhaps to our current level of O2. And it was during this period of time where we saw the emergence of plants and then later on forests and more complex life like we see on Earth today. I would like to point out here that even though usually when we think of life on Earth, we do think of this more complex life, is that the earliest evidence of life on Earth dates back to about 3.7 billion years ago. So even though you see a huge change in oxygen throughout Earth's history in this diagram, life existed for most of this diagram here, even when there was barely any O2 in Earth's atmosphere. So the question here is mainly just, could we detect these different O2 levels from different points in Earth's history? So to further explore how ozone content would change with O2, especially around different types of stars, I use for planetary atmospheric modeling, I use Atmos, which is a publicly available climate and photochemistry code. As you may remember, ozone formation is very dependent on incoming UV flux. So it's really important if you want to predict ozone content to have a photochemistry code that is really keeping track of the incoming light and how it's going to interact with molecules in the atmosphere. After I model those atmospheres, I use PICASO, which is another publicly available code. This one is a radiative transfer code, and I use that to produce planetary emission spectra. For the purposes of this talk, I'm going to go over my results for sort of the simplest cases here, which basically what I did is I modeled Earth-like atmospheres, and the only thing I'm changing in these models I'm going to show was the O2 level. So I modeled a big range of O2 level for Earth-like atmospheres around a variety of stars. So let's start off with Earth around the sun. What does the ozone O2 relationship look like there? So here on the bottom, on the x-axis, we have the O2 mixing ratios that I was inputting into the models. The mixing ratio just means it's the fraction of the atmosphere that is O2. And over here on the y-axis, we have a measure for the total amount of ozone in the atmosphere of each of these models. I've also marked with these vertical lines different amounts of oxygen corresponding to how much they are of this. Again, you'll see the PIL, which is the present atmospheric level of oxygen, which you could sort of think of these as different periods in Earth's time. So here at about 0.1% present level of oxygen, that would be, before the great oxidation event. After the great oxidation event, it's predicted that O2 was between 1 and 10%. And then more recently, with the emergence of more complex life, it was likely over 10% up to our current level of oxygen. All right, so if you look at this plot, right away you can see it's clearly not a linear relationship between O3 and O2. And what's perhaps most interesting is this sort of bump here, because you see that when there is a slight decrease in the amount of O2 in the atmosphere, you actually get a bit of an increase in the amount of ozone in the atmosphere, which at first definitely seems counterintuitive. However, if you look at the ozone mixing ratios for the atmospheric models I have at these vertical lines here with these different levels of oxygen, you can see, looking at the ozone mixing ratio, so you're seeing the amount of ozone for the different altitude layers, you could see that as there's less and less O2 in the atmosphere, it's actually that the ozone layer is moving down in the atmospheres to deeper layers. And the reason for this is because O2 does quite a bit of UV shielding. So when you have a little bit less O2 in the atmosphere, that means there's less UV shielding, which means the UV photons can go deeper into the atmosphere. So ozone formation mechanisms will take place deeper in the atmosphere. And what's important here is that certain Chapman reactions, which create ozone, occur faster at higher pressures. So if the UV can go deeper in the atmosphere because there's less O2 shielding, you can sometimes get more ozone because it's forming at a higher pressure. So let's see what this relationship looks like around different types of stars. Here I have the UV spectra of some stars that I modeled the Earth-like planets around. These are based off of IUE data, so this is real UV spectra. They were put together by Sarah Rugheimer. And this M star is actually one of the Mussels stars. So from what I've been saying about ozone formation and how it needs UV to form, we can probably guess just off the bat that these stars with more incoming UV are going to have more ozone than the stars with less UV. And that is roughly correct. So here we have basically the plot from the last slide with O2 versus total ozone. I've just added on the results for the other stars here. And just looking at it quickly, you can see that yes, the ones with more incoming UV do have more ozone, but looking at sort of the relationship between ozone and O2, you can see it's different for the different stars. You could see for a couple, you see this bump here again, where you see the effect where there's more ozone and then there's less O2, but not for all of them. So if we want to directly compare the ozone to O2 relationship for these different stars, it can be helpful to normalize them. So what I've done here is I've normalized each of these models to just what the ozone content is for that spectral type when I run the model with 100% our present atmospheric level of O2. So just this line here at 1 just shows that's the amount of ozone for that spectral type at our present level of oxygen. So you can see here for the hotter stars, so definitely the early G star, but also this K2 star a bit, you see the effect there where when you do have that initial decrease in the O2 mixing ratio, you do have more O3 for a bit. However, with these other stars, with the K5 and the M5 stars, you don't see this effect at all. In fact, as soon as O2 starts decreasing, O3 increases as well. So if we want to interpret the emission features of these different types of stars, we do have to acknowledge that the relationship is different for each of these. So for instance, if we were looking at a higher UV star like our sun, it's definitely very relevant to know that if we're comparing cases with 100% and 10% our present level of O2, the amount of ozone there, even though the O2 level is quite different, an order of magnitude different, it's still roughly the same amount of ozone that you would be looking at. However, if you're looking at one of the low UV stars, that wouldn't be the case. As soon as you start decreasing O2, you're decreasing O3. So let's look at some of the emission features. The main O3 emission feature in the mid-infrared is at 9.6 microns. So here you can see for the models I have been showing, just the different depths of the spectral features you would see there. And right away, you can see, of course, it's not linear, but you could probably expect that at this point. And you see that actually for the planet models around the sun, the deepest features are for both 10% and 1% the present atmospheric level of O2. So that could also seem quite strange at first, especially since although around 100 and 10% our present level of O2, ozone is about the same. For 10 and 1%, there's definitely significantly less ozone for the 1% level of oxygen case. However, the features are about the same depth. However, that can be explained by the fact that when you're looking at emission spectra, it is really the temperature profile of the atmosphere that's determining the depth of the feature. So in particular, it depends on the temperature difference between the emitting and absorbing layer. So when we're thinking about ozone, the depth of the feature is going to be dependent on the temperature difference between the planetary surface and the temperature of the stratosphere. So here for these models, we see the temperature profiles. And what's particularly interesting about ozone, if you're thinking about emission features, is that ozone is the molecule that's really responsible for stratospheric heating. So the more ozone we have, the more stratospheric heating we have. But unfortunately, that means that even though there could be more ozone, say if you look at the 10% case here versus the 1% case, there's more ozone at 10%, but that means the stratosphere is much hotter. And that means the temperature difference between the stratosphere and the surface of the planet is less than for the 1% case, which has less ozone, but a greater temperature difference. So it still has a feature that is just as strong. So that can be a little confusing. So we really do need to think about the photochemistry modeling and looking at the temperature profiles before assessing the emission features for a planet around a sun-like star. And also last, I'll show the same for one of those lower UV stars. So you may recall when we looked at the lower UV stars, as soon as I started decreasing the total amount of O2 in the atmosphere, O3 started decreasing as well. However, as you can see here, the two deepest features here are the 100% and the 10% O2 levels, which also might not seem very intuitive because those are definitely different amounts of ozone. There is definitely more ozone for the 100% present level oxygen case. However, again, there is still more stratospheric heating for the 100% O2 case. You will, however, notice that when you're looking at these temperature profiles here around the K5 star, that there is for all of them, even the ones with the most ozone, there's still not a lot of stratospheric heating there. And that's just because the star doesn't have as much UV, so it's not creating as much ozone. And since it is absorption of UV via ozone that heats the stratosphere, it's just not happening as much. So the emission features are still not very intuitive here, but interpreting them will be different than, say, around a sun-like star. So to sum up, if we want to do observing, think about biosignatures in the mid-infrared, we would have to learn how to use the O3CH4 biosignature instead of the traditional O2CH4 biosignature. The ozone to O2 relationship is nonlinear and it's highly dependent on the stellar UV flux for the individual planet. So we definitely need to do some photochemistry modeling there to understand the relationship. And if we're going to look at emission features, we need to think about the temperature profiles of those atmospheres because that's going to be determining the depth of these spectral features. And with ozone in particular, that can be complicated because ozone is the main molecule heating the stratosphere, affecting the depth of the feature. And lastly, I'd like to say that since this isn't a live talk, so I can't take questions at the end, if you're interested in this work at all or want to chat, if you're in the Life collaboration, you can contact me on the Life Slack workspace, or you can email me and there is my email right there. So thank you so much for your attention and please don't hesitate to reach out.